All right, how we doing, everyone? Doing good? Assignment's going good? Today is Monday, October 25th, 2021. I'm re-recording this video from Friday's lecture, which kind of got lost, but don't worry, we will go over the total response of analog and digital systems. So if you've realized it from the last lectures that we have computer assignment 1, which actually I'll talk about that right now. CA1, which basically gives you an intro to MATLAB. So everyone here can like program like really simple signals, right? Not convolve, but just generate signals, right? And you have CA2, which is basically, okay, now you have these actual definitions like definitions and like the Dirac delta and the unit step and all those other cool stuff, right? And difference equations too. Right? Remember that stuff? We were trying to do all these like for loops, for I is equal to something something, y is equal to b0, x of 0 plus b1, x of n minus 1 or something like that, dot, 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 right? That was the whole purpose, to get you guys like, oh, for loops, we were actually implementing these and difference equations and just letting them run. And you have CA3. The computer assignment 3 is basically the intro to convolution, right? And then we remembered, okay, we have those difference equations, right? This right here is like, it's a lot. It's a lot to write. So instead of doing this and programming this, why don't we just do something crazy like, oh, we have an h which is constant. This doesn't move, but we convolve this with some vector that does move, our input. We can just sample our input from like, oh, from beginning to end, or sample it. Just sample a couple points so that we can do this hardcore definition of convolution, and that makes everything really easy. Now, computer assignment 4. This is the big point of this class. This is the like total response. And the total response is basically if we have some system, a system that's input, output, and has, well, some stuff in the middle. What is the system's response due to it just having some kick? And I will use a different marker for that. Some kick, the delta function, also known as the zero state response. So when we have no memory in the system, what does our system do when we just kick this box? Okay. And then the other part is, okay, we have our system. It's built. But let's say it's got memory in it, like memory. Then what is the response due to no input? So ZIR. So there's no input. We're just looking at the memory. What's the output? But then when we add these two together, pull up the good old red marker, this plus this, we get a total response. And this is basically by linearity. If we can just add a zero input response, so there's memory, add the stuff where we have memory in a system, plus the response due to an impulse, just kick the box. There's nothing, there's no memory, we just kick it. What does it do? By linearity, we can add the two and we can get something really nice, the total response of any system. And the whole point of getting to this 4th assignment is, well, everything you can do right now is you can build any system. And that's the beauty of this assignment. So, yes?
I thought you were supposed to convolve them.
Convolve them? Oh, no. The outputs. So you have the zero input response. Actually, I'll explain it on another piece of paper. I know what you're talking about. Let me see. So let me build a system for you too. So let's build some system. Feed forward and feed back. Okay, some X input, and let's call it some C of N input right there. And some Y output. So when we're doing a zero, let's talk about zero input response, okay? We're doing a zero input response. So that means this right here, okay, if we're doing ZIR, what's a zero input response? Our input is 0. if I were to design a feed forward path, so remember all those direct form blocks, direct form 1, 2, and transpose 2? So if we were looking at this as a direct form 1 block, how can we model this feed forward path? We can model it as, let's go a node, and just do 2 nodes for now. D, B0, B1, B2, add, and this right here is a feed forward, okay? This is our feed forward block. All our things go forward. So if we're right here, right? And we kick this right here, right? What do we get if we put like some delta function here at times n is equal to 0? What do we get at our output? Be a 0, D, I'm just gonna do this for now, right? Okay, to make it more sense. At time 0, we have a 1 right here, right? And since we have no memory in our system, right? What do we have right here? 0. Then what do we have here? 0. So we have a 1 times this, we get B naught and the delta function. Then what do we get here? Nothing.
0.
Nothing right there. But now let's say we move another time, right? Okay, now this is 0, right? But now the 1 has shifted down here. And then this is 0, right? Now what's our output? So this 0 times B naught, 0. But now we have our 1, our delta function has just moved by 1. So what are we going to get? B1 plus, times this delta function n minus 1 because we moved in time, okay? And then this is 0. And if we do it again, I'll use another marker for that, black marker. This is a 0, it's already moved. And then this is already a 0, and now our 1's down here. You see the pattern? And it feeds forward. This is also known as your finite impulse response. So basically, if we throw an impulse in here, and the output is, well, it just what do you call it? It's finite because everything feeds forward. Everything goes forward. It doesn't come back at itself. If you throw something here, it just gets spit out in the output. All right. So if you think about this, if we have an impulse, if we're building just this part, if you're an engineering company just building this part, and I say, okay, just design me a feed forward or FIR filter. This right here, what is your impulse response due to just kicking your box? This. Does that make sense?
Why do we call it H0?
So that's a key word for what we'll talk about in the Laplace transform, where, okay, I'll give you the surprise. So, okay, we did talk about the Laplace transform. So you from 221, where remember we had some h of s is equal to s plus 1 divided by s plus 2. You notice that this right here is zeros, and this right here is poles. Remember from 431 or 432 math? So that's the surprise you're trying to like, shh. So that's the reason why we call them zeros. Well, they don't blow up. You throw something in here, and if you put like a 0 or any number into s, it doesn't blow up. But we see right here, if you put this s to a minus 2, oh, it goes to infinity, the entire thing. So before I get into that, you understand that, okay, if I were to tell you to design me a feed forward path, just a feed forward response, or just a system, what is the impulse of this feed forward block? Got it? All right, and that's our H0s, okay? We just built part 1. So building part number 1, okay? So we just have our own system. We can take this piece and move it anywhere we want. We can build it into our senior design projects or whatever we want. So now the next thing I'm going to tell you is, okay, now we have our feedback path. Remember from the direct form block 2, okay, if I wanted to, no, I'll just do this. C of n, and the reason why I'm teaching it like this is because I want you guys to think of it like engineering parts. This is not math. This is just, we're treating it as like things we can build. Okay. D, and let's make this D, and I think that's enough. Okay. Minus A1, minus A2, add, and go there. Okay. Now y of n. All right, you see that? So you're an engineering company. I tell you, okay, so ignore this feed forward path. Okay, what we have right here is you're designing a feedback circuit, okay? And I tell you, okay, we're gonna have some input and it's gonna go into an output, but we feed this output back into the input, okay? It's feedback circuit. So I want you to build this part, okay? What is the impulse response of the system? And how do you start these problems? How do you find the impulse response? Just kick the box. Here, you just put a delta function in there, okay? Treat these as parts, okay? So I'm gonna use a different marker. Okay, this is the mindset I want to get you guys prepared for the exam. So we're treating this as part number 2, okay? So we just kicked our box. We have a 1 in here, okay? So at time n is equal to 0, what is y of n is equal to 0?
1.
Just 1, okay? And assuming, yes?
Wait, hold on. So when we kick our box, is it always going to be 1?
Yes, it's a delta function. However, actually, no, I'll talk about that later.
Automatically, like, kick the box 1.
Yes, we're just thinking about a delta function itself, the impulse response. The definition of the impulse response is, where do I want to write this? I'll just put it right here. Impulse, actually I'll just write this, is response to delta function. Okay? And you know what the delta function is, the Kronecker delta. It's just a 1 at time is equal to n is equal to 0. But the Dirac delta is infinity with a really small width, but I'll talk about that later. But okay, point is, we're looking at a feedback circuit, okay? Is everyone understanding this? Feedback circuit. I tell you to build this part, and now I ask, what is the impulse response, okay? What is an impulse response? A response to an impulse, a delta function, okay? At time n is equal to 0, what's the output? 1. And since we have no memory here, what's the value here? 0 and then 0, right? We just kicked the box. So now the next thing I'm going to do, okay, now 1 second has just passed. Okay, now this right here is, let me just color this red. 0, okay? And now where's the 1 now? The 1's down right there, okay? And then this is 0, all right? So right now we're about to do some crazy math. So what is the, okay, so let's start right here. We have a 1 right here, right? And that 1 goes into this minus alpha 1, right? And then it comes right here. What is y now? Minus alpha 1, okay? Got it? And this is a 0 multiplied by this, and that's it. We're done, okay? So now, what I'm going to try and get you guys to learn, so we have something in our output right now. We have, let me circle this. We have this right now in our output, and this is right now at the current time we're working, okay? So this is what we have at this time, right? Now all we're going to do is just chunk this down, and I'm going to do the following, and we're going to use a black marker, and where did I put it? Come on, should I use this green marker? Let's try it. Let's use the blue, I guess. So we have an alpha 1 right here, right? And we minus alpha 1, and we have a 1 right here. The 1 now moves down here, okay? But this also moves down here. Okay? You're seeing that, right? So now what's our output now? So we have this 1 that times to a minus alpha 2, right? Minus alpha 2. Okay? And now we have a minus alpha 1 right here, right? That gets multiplied to this minus alpha 1 right here, right? Got it? So minus alpha 1 times minus alpha 1 is alpha 1 squared. Okay? And then you start seeing this weird pattern where now you have this term, actually let me use this marker, this term here, this term in your system, and this term in your system. And now it's just doing this like infinite loop where it's just adding on itself. And this right here is an infinite impulse response. So I, R, okay? Because it's just adding on itself all this time until it just gets to hopefully 0 or it stabilizes. So what I'm trying to get to you guys is to approach this problem, and we'll just get to the practical stuff right now. Let me explain this. So remember how I said we're going to treat this as just an engineering part, right? So if I were to model that circuit, let's do it as, let me think. If I were to do this, y of n plus a1 y of n minus 1 plus a2 y of n minus 2, right? Okay? So what I'm saying is, okay, we have just a feedback circuit, right? We're looking purely at the feedback circuit, treating this as an engineering part. We have no feed forwards. What does this mean when we have no feed forwards? We have no B0 terms or B terms. What does this look like? The auxiliary equations. Remember that from the last assignment? This, you see? Now we can start treating this as stuff we've already remembered from the ZIR. So how do we approach these problems? So, huh? This equation? Okay, I knew someone would ask about that. Huh? Okay, because I'm doing this. Y of n is equal to minus a1 y of n minus 1 minus a2 y of n minus 2. Here, y of n is equal, it's also equal to, okay, well, I'll just question that for now. Y of n is equal to minus a1 y of n minus 1 minus a of, or minus a of 2 y of n minus 2. That's where I got this equation right here. So what I'm trying to get to you is, this looks really familiar to what you guys did in the ZIR. You're doing these auxiliary equations. And then all you do is just, okay, you can just replace this with, does it bother you if I just skip steps? Lambda squared plus alpha 1 lambda plus alpha 2 is equal to 0. And then you guys can solve for your auxiliary equations right there, okay? Does that make sense?
Whoa.
You seem a little
Is
confused.
it y sub n just lambda?
Y sub
But it's squared.
lambda squared?
Oh, by 2.
Yeah, I'm just skipping steps right now.
Ooh, don't do that.
You don't like that?
No. I gotta pass.
Wait, on the exam, we're not gonna get like one like from the computer side, right?
The one on the computer assignment, no, you're not going to get the computer assignment one because,
For lambda, like, yeah.
no, that's painful, okay? Don't do that. But what we will try to do is, I want to go over one thing.
Okay, I see it now.
So for exercise 1, I'm asking everyone to find the 0 state response of the system, all right? And if you looked at this, let me see. I don't want to show you guys. I'll just build it for you guys on a second piece of paper, 3. But let's look at the poles first. So I'm going to get these poles right now. So y of n minus 2r cosine omega, y of n minus 1 plus r squared, okay? All right, hopefully I don't waste so much paper today. Yep. Come on, there we go. Sweet. So what did we have? Y of n minus 2r cosine omega naught, y of n minus 1 plus r squared y of n minus 2 is equal to 0. All right, so what I'm going to do, oh, there you go. What I'm going to try and do is we're going to treat this right here, this feedback path, as purely its own part. Okay? So how do we solve for this stuff? Just solve for these auxiliary equations. Remember that stuff? And then we can just, okay, because someone doesn't want me to skip the steps, remember that lambda trick? Lambda, or not like this, y of n minus n. We're going to replace this with lambda to the minus n. Yes, minus n. All right? We're going to place all these y's with this lambda. All right? So look at that right here. We have a lambda to the 0 because there's no delay there, minus 2r cosine omega naught, lambda to the minus 1 because we have a minus 1 delay there, right? Plus r squared lambda to the minus 2 because we have a minus 2 there is equal to 0. Okay? And now the next thing is you got to learn this DSP trick. So here's cosine, right? Cosine omega naught. We're going to go into Euler's equation, which basically states that this cosine omega naught, we can replace this with its exponential term, which is e to the positive frequency, e to the positive j omega, plus e to the minus j omega, so positive frequency, negative frequency, divided by 2. Why divided by 2? Because if you look at the Fourier transform, you have like this, well, that's another conversation for another day. 361. You'll take that next semester. But right now we're going to look at this. And we're going to replace this into here. So before we do that, do you want me to skip steps and just multiply the entire thing by lambda squared?
Yeah, that's fine.
Okay, and then I'm going to replace this into there too. So lambda squared minus 2r, I'm going to put the lambda right in front. Do this, e to the j omega positive. I like putting the positive there because it gives me sanity. Plus e to the minus j omega divided by 2 plus r squared is equal to 0. All right? So what I'm going to do is, okay, you see that 2 right there, right? Gone. Boom. Done. You don't have to worry about it. And what I'm going to try and show you now is lambda squared minus r lambda e to the positive j omega minus r lambda e to the minus j omega plus r squared is equal to 0. So there's a trick I looked up, and there's this thing called decomposition where, let me see from my quick little notes that I have right here. Let me see which one I actually remove. Did I do that? Let me see. Yeah, I think we'll figure it out right here. Where we're going to play with this. One of the things I want to substitute out is this lambda right here. Right? So if I were to pull out a common term from here, let me see if I can do this right. From this term here, I can pull out one lambda. And what do we get here? We get a lambda minus r e to the positive j omega. All right? So I'm just pulling this lambda out. All right? And let me see, because I can play with this right now. Here's the r. I like that. What I'm going to do here is I'm going to pull out, and I'm going to show you guys, hopefully you guys don't get confused. I'm going to pull out a positive frequency from here. So I'm going to do this, where I'm going to do plus e to the positive j omega. I think that's it. No. Let's pull out a minus. Okay? And I'll show you what I mean. So lambda. Let me see. Hold up. Why do I have this? Give me a moment. R e to the j omega. Nope. We got to pull an r. Sorry. Pull an r. Keep the lambda. Here's this. Minus e to the
Negative.
Positive j omega. No.
My bad.
This is a positive. Minus. This is a minus. Hold up. So right here, right, I'm pulling out a lambda. Okay, and our resulting thing is here. What I'm trying to get to you is this, I'm going to try and get this to mirror here. So what I need to pull out is, I need to pull out the negative frequency. Minus r e to the minus j omega.
Oh, okay.
Okay, so if I pull this out from here, I'm gonna get a, should I do this? Okay, let's do a positive. Positive r, is it gonna be a lambda? No, a lambda, positive lambda, yes. Minus r e to the positive j omega. Okay, so if you multiply this back into here, you're gonna get this resulting back. And if you multiply this right here, you have a minus frequency times a positive frequency. When you have a positive and a negative frequency multiplied together, you get 1.
Okay.
Well, you get the r squared, r times r, r squared. And that's this dot decomposition. And now that we have these two terms in common, we can just factor this out to give you the two poles, which is, see this right here? This right here? Lambda minus re to the positive j omega, the positive frequency. Lambda minus re to the minus j omega, the negative frequency, is equal to 0. Therefore, lambda is equal to re to the plus or minus, plus, is that how you write it? Plus minus j omega. And that's how you find those poles, the whatever characteristic equations. Does that make sense? And we're using decomposition. This right here is called decomposition from algebra. Just in case you want to review this on Purple Math or wherever you guys want to get that from. Huh? In 480? Yes. You actually go over this again in 480. Yes. So the thing I'm trying to play with you is stay in your Euler's domain, the exponential domain. It's really, really useful. So just in case, look up decomposition. Instead of doing that quadratic equation, it's painful, do decomposition. Much easy. All right? So now that we have our characteristic equations, this is page 4. Pull out page 5. So one thing I need to stress out a lot right now is we're building an engineering part, right? We're still building this feedback path, okay? C of n and y of n, okay? So the guess that we're going to have to make, y of poles, okay? Y poles, right? Is going to be in the form of, should I write it general or just get to the point?
Whatever you think is best.
Okay, C1 of, let's see, let me think about it. Oh, lambda to the, no, I don't like that. Lambda, yes, lambda to the n plus C2 lambda 1, lambda 2 to the n. Okay, our guess is this coefficient right here. We have some C of 1 times our lambda, which is our actual pole or thing, to the nth power. That's our guess. We're just guessing right now. All right? And then we have a second one because we have two poles. We have two things we got to mess with. So what I'm going to try and stress everyone right now is, let's see if I can build this for you guys. D, because it's second order. And then, you want me to skip steps on this one? Okay, I'm going to show you this. I don't want to waste too much time. Minus r squared. And then this right here is positive 2r cosine omega. Okay? I'm just building something for you guys. Okay? We're just building this. So what I want to stress out for you guys, for the zero state response, so that means there's no memory in our system, we have that kick, right? Into our system, right? What is the value here? Here's y. What is the value at n is equal to 0 at this point? 1. Okay? So this is what we're going to do. We're going to put into our system. You know that, Alright, so that means if we were to do this, y poles of n is equal to 0, right? That's what we're going to do. We're just building this part and we're putting a 1. This is your condition for impulse response of feedback, digital. Okay? So this is what you're going to remember on the exam. This is like the easiest thing you can actually remember. So when you're doing a zero state response, there's no memory. So this is 0. This is 0. We kick our box. What is our condition? 1. That's always a guarantee. All right? Which is equal to C of 1, lambda 1 to the 0 plus C of 2, lambda 2 to the 0, right? Which is equal to C1 plus C2, and C1 is equal to 1 minus C2. Got it? And then one thing I didn't do is this. YP is equal to C1, and where my piece of paper? I'm going to do this. RE to the positive j omega of n. The entire thing is n. Plus C2 RE to the minus j omega of n. Okay? So we just figured out this one right here, right? Alright, so now what's the next number we got to do? Y of p of n is equal to minus 1. We're just ticking time, okay? We're looking at n is minus 1. N is equal to minus 1. Okay? Which is equal to 0 because there's no memory in our system. We're just looking at, okay, we have a 1 here, we have a 0 here, we have a 0 right there. Here's y of 0, y of minus 1, y of minus 2. Okay? So this is our condition that we have. There's no memory. We have this kick here. This is how we solve for this. Here, we have n minus is equal to minus 1. We have a 0 there. Which means we can do the following. C of 1, and does it bother you if I do this? R to the minus 1, e to the minus j omega. Is everyone following that? Plus C2 R minus 1 e to the positive j omega. Is everyone getting that? Because I don't want to waste too much time, get rid of that. And now we're going to solve for one of the coefficients. So what I'm going to do is just punch this into here. Okay? So now we're going to get the following. I'm going to skip some steps and do the following. E to the minus j omega minus, let me see, I just put that there. C2 e to the minus j omega. So I'm looking at this term times this entire thing right here. 1 minus C2 times this. All right? Everyone see that? Plus C2 e to the positive j omega. Okay? All this is equal to 0. So the next thing we got to do is, okay, we want to solve for C2. So what I'm going to do is, let's see, should I do this? I'm going to do it on another piece of paper because this is a lot of work. Okay, 6. I'm going to put this on the other side and I'm going to factor out C2. Oh. Okay. So if I were to do this, minus e to the minus j omega is equal to, let's do this, C2 minus e to the minus j omega plus e to the positive j omega. Okay, I just moved the term to the other side and factored out a C2. Okay, and now to solve for C2, and I'm going to put the positive frequency here. Okay, so the one thing I'm going to tell you right now is you could just like multiply some exponentials away and get rid of these things, but no, these are your best friends. Here you have the same frequency, like 10 hertz, 10 hertz, 10 hertz. Keep it all the same speed. Don't manipulate the speeds of this exponential. So we're going to go into our little DSP world and remember our rule for sine. And do it like this, sine of phi or something like that, which is equal to e to the, let's do this, phi of j phi minus e to the j phi. I'm just doing this as a coefficient. So we have a positive frequency, right? Minus a negative frequency. All divided by 2j. So this is something you'll eventually see in 361, but for now, this is what we're going to be using to solve this problem. So you see this right here, right? We have a positive frequency minus a negative frequency. When you see this pattern, you see a positive minus a negative frequency, think of sine. When you see a positive, let me see, where is it? When you see a positive frequency, a positive plus a negative frequency, think of cosine. And then the only difference is there's a j in sine. Okay, that's the trick I'm trying to get to you guys' brains. All right, so you see that right here, right? So how do we get that 2j to like work with us? I'm gonna put this 2j right here, 2j right there, right? And then if you see this right there, right, we can replace this with sine. And I will just do this minus e to the minus j omega divided by 2j sine omega naught. Make sense? And then for C of 1, we stated that C of 1 is equal to 1 minus C of 2, right? Is equal to 1 minus minus e to the minus j omega 2j sine omega naught. Okay? So we could have kept this, but I'm going to replace this term right here with this term. Okay? So this right here is equal to this, right? But I'm just going to put this right here back in here. Okay? Okay?
Wait, I'm sorry, what did you just say?
So, okay, you know how this right here is equal to this right here? So, and here it is, right? But this kind of looks a little weird, right? We have exponentials and sines, and that kind of looks scary. But what did we do? We like to work with Euler's equations, these exponentials. So instead of working with this, I'm just going to go back to here. So I'm kind of going back a little bit, but this is clean to see. But we're going to go back here because we need to work with this. We got to work with this 1. So we're back here, okay? See? So what I'm going to do is this term right here, right? I'm going to multiply this to this. And then you know this is 1 divided by 1. When you cross multiply, well, we're trying to get a common denominator, okay? And now, hopefully I printed enough paper. 7. After doing this little multiplication, we're going to get the following. C1 is equal to e to the positive j omega minus e to the minus j omega, okay? And this is minus e to the minus j omega, all divided by e to the positive j omega minus e to the minus j omega. Okay? And then we see this right here as a plus, right there, right? And then this right here cancels out with this right there. And all we're left with is e to the positive j omega divided by e to the positive j omega minus e to the minus j omega, right? And then remember that little trick, 2j, and let's do this, right? Which is equal to e to the positive j omega divided by 2j sine omega naught. And there we go. Now we have C2, which is minus e to the minus j omega divided by this. And then we have C1, which is the positive j omega. Ah, see, that's the reason why I wrote this, because it's easier to see. Cool, right? And now, oh, I tapped on the microphone. Now we can punch in for our poles. Y poles n is equal to, I'm going to use the big red marker. Okay, C of 1 is equal to e to the positive j omega 2j sine omega naught. And then we got to get its eigenfunction. Where is it? Page 3, page 4, page 5, got it. I'm just replacing all the C1s and lambdas. Well, here it is right here. I'm just replacing C1 and C2 into this, right? R e to the positive j omega to the nth power. Okay, this is the lambda. And this right here is our C of 1. And then plus, now we got to get C2. Where's C2? Which is this right here, okay? Minus e to the j minus j omega divided by 2j sine omega naught. Okay? At C2. And then we got to get its little lambda. What is that lambda? R e to the minus j omega all to the nth power. All right? And then if you see a pattern, let's see. What I'm going to tell you right now is you see this j omega right there? We're going to multiply this into here. Okay? So what I'm going to try and show you on another piece of paper is we're going to multiply this j omega, e to the j omega, to here. And what's that going to give us? Here's an n, right? So it's going to give us n plus 1 j omega. All right? So doing that again, yp of n is equal to, you guys want me to pull up this r of n?
Yes.
Okay, I'm going to do that right now. R of n, I'm just going to do, because I don't want to skip too many steps. And I'm going to do the following. E to the j omega n plus 1, okay? And minus r of n 2j sine omega naught. And then same thing right here. Here's a negative j omega adding to another j omega to the nth power, which should give you e to the minus j omega n plus 1. Right? And then you start seeing some patterns. Here's a r of n, here's a 2j. R of n, 2j sine sine omega naught, and then e to the positive j omega n plus 1 minus e to the minus j omega n plus 1. All right? And you remember that cool thing we were talking about? That Euler's equation? Here you have a positive frequency and a negative frequency, and we're taking the positive frequency and subtracting it with a negative frequency. So that means we need a 2j, right? Here's our 2j. Okay, so we can just take this. You seen that? R of n sine omega naught sine omega n plus 1. Y poles n. And put the u of n here too, to tell us that we kicked the box at n is equal to 0. All right, and that right there is actually the impulse response of the feedback path. Does that make sense? So to recap what I just said, you're an engineering company. You're at an engineering company, and I told you to build me a feedback circuit. Here's your feedback circuit. What do? Okay, you develop these equations, which I will show you right here, right? And this looks like your auxiliary equations. You get your lambdas, okay? Once you got your lambdas, now you got to do your educated guess. Or, let me see, where is it? Educated guess. All right, C1, lambdas, right? We kick the box at time n is equal to 0. What does that mean? We have a 1 here. You got your condition. Memorize that, okay? And now just solve for C1 and C2 until you get to the part where you're right here. And guess what did we do? We kick the box. What's that kick equal to? It's the impulse response of the feedback circuit. Now you can take this part and put it into any project you want, senior design, whatever you want. Congratulations, you just build a feedback circuit. Now, time for the pinnacle of this class, the biggest part. This is page 8. So now, you build a feed forward circuit and a feedback circuit. Now put them together. Wait, oh. Feedback. So you just built this part and you just built this part. This right here is our H zeros, right? This right here is our H poles. Here's X of n, C of n, and Y of n. So remember that exam and that everyone got this circuit. Here's H1 and H2. But he says, all right, determine the impulse response of this system. What does that mean when we have an impulse response? Our input is an impulse, which means this right here is that. But we just designed this, right? What happens when we convolve this with an impulse? What is C of n? Convolve the anything with the impulse, you get the anything back. Right, boom, done, 5 points, done. You see? That's knowing your definitions from chapter 1. All right? And now you have this right here. So this just gets shifted down there. Now you have this signal going with this. What is Y of n? Or H zeros convolved with H poles. Cool, right? And all we did is we kicked this box. This is gonna give us some signals. We built this part, but now we're putting it back in here. This is gonna generate a bunch of Dirac deltas or Kronecker deltas, and it's gonna feed into this circuit. How do we do that? Use convolution. Cool, huh? So, recalling what we had. Let's see. Well, we just solved for the poles, but you know how to solve for the zeros, right? Okay, I'll build it for you. Someone's probably arguing about it. Where is that circuit? Right here. So what do we have at our input? Just R sine omega. So I'm going to build it for you. Okay. Nope, not that way. Let's put one delay here. And we just have an R sine omega naught. Okay? So what is so we just kicked our box, right? What is H of zeros? What's H of zeros? Does that make sense? You getting it? All straightforward, right? So this is our new signal. This signal is going to convolve with our poles. R sine omega naught convolved with our poles, which is R of n divided by sine omega naught sine omega n plus 1 u of n. Okay? So what happens when we convolve a delta function with anything? We get the anything back. However, this is telling us, hey, delay this. So all the n's get delayed. So I'll do the following. So r sine omega naught is a constant. It's some coefficient. It's just a number. And then this, okay, actually, here's the sine omega naught right here, right? I'm just going to pull that down here. Okay? And then what we're going to do is we're going to shift all this, all the n's, by 1. So r of n minus 1, sine of omega, here's n plus 1, it just turns into n. Okay? And this u of n turns into n minus 1. And then you start seeing the pattern. Oh, this r can multiply here. This cancels with that. Then, all right.
Aren't you forgetting
N minus 1
for r? Yeah.
for r. I already have that here. R there. I delayed this r, this n, by 1. This right here got delayed, and this right here got delayed. This r is multiplying into here to give us that just n back. Okay? So you see this right here, right? Here's our zeros and here's our poles, right? What is this total system? This right here is h of n, the total, not the total response, the ZSR or impulse.
Oh, that's just it. Okay. Just the ZS.
And congratulations, you're done. So, how do you prove this? You prove it in MATLAB. So, actually, should I go in the MATLAB or should I try to cover ZIR a little bit? I'm gonna do the quiz because honestly, it's already almost 6:30, so we definitely got to talk about that analog part. But point is, you guys all do quiz 6, right? Let me show you. So actually, before I talk about that, yes, this is your answer to exercise 1. So if you can do all this, did you see how much work this is?
Yes.
That's why it's worth a lot of points. Do you understand how to do this? Is everyone gonna get hundreds on this assignment? Easy peasy, lemon squeezy? Perfect.
Wait, so in the exam, is he gonna give something like with cosine and stuff?
Cosine? No, I don't think, no, he's not gonna give you, he's just gonna give you 1s and 2s and just gonna put your numbers. Now exercise 2, okay? So how do you prove that this system is stable? Y of n is equal to h of n, x of n, or h of k, n minus k, k, positive. We use this Schwarz inequality, but he also calls it the other thing because what he's trying to do is, okay, if we have unstable input, we don't have to worry about the stable input. We can just worry about this summation of the output. Okay? So how do we determine if this system that we just built is stable? Well, just do this. Let me see. R of n sine omega n u of n. Okay? Right? But right here, we have this right here, right? This right here is saying, okay, you can't, our function is going to start at the time of n is equal to 1, which means this right here is going to equal 1, k is equal to infinity of, let's just scrunch that in, r of n sine of omega n. But you know that sine just goes up and down, it doesn't do much. But you see this r of n, right? What happens when this, or not r of n, this is r of k, 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 there we go. Sorry, right? You see this k, right? If it goes to infinity, right? Then we have to look at what r is going to be. So that means, how do we make it stable? What value of r should we have for this system to be stable? What if r is 2 or 3? 3 to the infinity power, right? It's going to be infinite, right? So what value of r do we have to have for it to be stable? Can you prove stability? That's it. Yes?
Wouldn't sine, like the absolute value of sine, wouldn't that be an infinite area?
Yeah, you're not wrong there too. And I had a problem with him too. I was like, but Dr. Steve, it's going up and down, and you have positives and minuses adding together. But he was like, oh, it's unstable. I'm like, I don't know. But don't worry about this. I'm looking at this r for now. Okay, so the assignment literally, like, the first part is a lot. I'm grading a lot on the first part. Basically, do you understand this assignment? That's all I'm asking. And then example 2 is, do you know how to make sure it's stable, right? But okay, if I wanted to, I'll run this right now, MATLAB, and I'll show you what we did last class, okay? So you're saying, oh wow, oh my goodness, we just solved for an impulse response, right? How do I know it's right? You can type it into MATLAB. And, oh, where's my mouse? There it is. And we did some work last time, and I can't see that. How to change font preferences. Font 18. Okay. There we go. So remember all that stuff we were doing in this assignment 3, right? It's all easy. We've done difference equations. I've trained you all to be able to do ZIRs and ZSRs, easy peasy lemon squeezy, right? And you're probably looking at this like, oh, we did difference equations. I don't know. Does it look right? Remember this from the last quiz, quiz 6? Remember that? ZIR, we proved it by hand calcs, and we even did the direct form block. Last assignment was ZIR. This assignment is ZSR. So, right, you want to know how okay, so what I did is I literally plugged this equation into MATLAB. And that unit step right there, it's delayed, right? How did I make that unit step? Let me drag this puppy right here. You know how your unit step right here has like, oh, it has some zeros, right? I gave you that code, right? Here's a 1 and it has 1s, right? So how to make it delayed? I just place this 1 with a 0, then I put the 1 there, and then there you go. But you have to subtract the 1 to get that delay, all right? Let's see. There's one thing I'm gonna try and check out. Test. Volume can be okay. Wait. Before I get panicked about it. Hello, test. 1. All right. We're still recording. Plug in your hand calculations. What are you gonna get? Here's our total response. Let me do this. Editor, run section. So right now we're running the difference equations. That's your difference equations. Oh, I gotta change one thing. Oh, by the way, what happens when you make r something greater than 1? It gets unstable. Unstable, sorry. 0.9. Run section. You get that, right? That's your difference equations. Yeah, that's your total response. Don't worry about that. And then right here, I'm gonna run this. This right here was from your quiz 6. Remember that? And the solutions are in the books too. Remember that? So right now I'm running this equation right here. So that's stuff that we did on our hand calculations. Okay? And then this right here is what we calculated today. Run enter. Doesn't that look good? And then you can verify this with your difference equations, stuff you've already been used to. What I did right here is actually did a total response. Let me show you. That's your answer to your the total response of your entire system. Like you're saying, why does it look like this? You're adding the ZSR, the ZIR, it just doubles. See right here? Here's the top part, 1.42. This right here is your ZIR, it's like 0.7. Here's your ZSR, which is also 0.7. 0.7 plus 0.7 is 1.4. Got it. And then, yes?
So why is zero state response the same as the 0 and 1?
Because Dr. Stewart planned this assignment, so it's really trivial and to make sure you understand what's going on. So basically,
That won't always be the case.
it won't be always the case. I could have changed the assignment, but I'm like, yeah. I could have made it the book solutions too, but you have another problem you can work on. But point is, someone was asking, why does the ZSR and the ZIR look the same? Because it is. But you get two different equations. Here, you get a delay, and here, you don't. It's pretty interesting, right?
What's the relationship between the zero state response and total response?
So that's zero state response and a zero total response.
Yeah. The total we're just adding them.
Let me show you.
You're just involving the
So the total response, and that's the what okay, this is what I had to hammer for you guys. So the total response of any system is taking the ZSR, the kick into your system, no memory. Okay, there's no memory. We just kicked the box. It's a lot of work to get this impulse response. It's whatever we did here. We just kicked our box. We just bang this entire system. Zero state. There's no memory. We just kick it. Plus ZIR, where we have memory. So that basically is, okay, if we have a 0 right here, right, at the feed 4, right, 0 times this is 0, right? So all we're looking at is the auxiliary equations. So the auxiliary equations, which are defined as this, right? But for the ZIR, this is something Dr. Stuber will give you. He's going to give you a memory. So he's going to give you an equation. Where's page 5? Let's see. Page 5. Let's see. It's 8, 5, right here. This condition is for the impulse response of the feedback circuit. So right now I'm just going to do something really random. Y ZIR N is equal to C1 lambda 1 of n plus C2 lambda 2 of n, right? Where he's going to give you y of 0 is equal to memory. So whatever Dr. Stuberud gives you. Okay, so this is stuff you have to work with. Whatever number he gives you for your memory, your ZIR, he's going to give that to you. You just solve it the same way, solve for your ZIR. Simple. And then you add the ZIR to the ZSR, and you get the total response. And, analog example of this.
Yeah, just simple numbers, first order.
Your quiz is marked out, right?
Yes. Let's just go over that quiz, which everyone will hopefully turn in for me. But you're understanding what the total response is? All right, cool. Can't waste time on this anymore. You got to go into analog, because this is the part that's going to hurt a lot of people if you don't understand this. I will promise you. And I remember Haley, she was in class. I was like, oh, no, don't worry. It's hard. But the way I'm going to show it to you guys will make sense. And if you don't memorize the procedure I'm about to show you, it's going to bite you on the exam when it gives you a second order equation. So when you're doing an analog problem, and I'm going to go over your quizzy. Let's look at this right now. And I want everyone to tell me if it's making sense. So we have this analog problem, which may or may not be on the exam. He might make this a second order equation, but I'll show you exactly how to tackle this problem, and it should be simple. Okay, consider an analog system, and I will just put in this number. Let's just solve it right now. analog. So dy t dt plus 3y of t is equal to 2 dx of t dt. Gotta put my microphone closer to me. Plus 4 of x of t, okay? So solve for the zero state response of the system, all right? So actually, is that what I asked for? Yes. Actually,
You asked for the total.
the total response. Okay, so when you're tackling the total response of any system, the tip I'm going to give everyone in here, practically when you're in this exam, solve for the zero input response. It's the easiest. So what I'm going to show you is, for now, let's use a model. I'm going to do a model. Oh, gotta tell me about that model. So what I'm going to do is I'm going to turn this into its integral version. So all I'm going to do is just integrate the entire thing. So if I were to do this, I'm going to get y of t plus 3 integral of y is equal to 2x plus 4 integral of x. Okay, right? This is just a model. So what I'm going to do is, if I have my input, let's see. If I were to integrate this, and we have, okay, let's see, let me think about this. The 2 feeds forward, the 4 gets integrated, okay? Is our output. And then, if I were to integrate this, I'm just going to do this as a model. 3. Okay? So for your zero input response, all right, just have a 0 in there, right? And the memory condition I give you guys is, let's see. Okay, before I talk about that, if we have a 0 at the feed forward, okay, what's our value right here when we have 0 times this? 0. And then we have 0 times this. Point is, what I'm trying to tell you is, when you're doing a ZIR, this goes away. All you're going to focus on is just purely this. So purely this. So what I'm going to show you guys practically to get you out of here is just focus on your poles. Okay? So the trick that we're going to apply right now is, every time you see a d to the n y divided by d of t to the n, replace all these derivatives with lambda to the n. Okay? To get the following. Lambda to the 1 plus 3 lambda to the 0, okay, is equal to 0. Because we have no feed forwards. It's just nothing. There's 0. This comes from here. Okay? This is how you're going to do it on the exam. And if we had a second order 0 or second order pole, you would have another pole like, oh, this would be, if you had d2y, a second derivative y plus a first derivative, same thing. You're solving for these auxiliary equations. Okay, this goes away. Lambda is equal to minus 3. Just solve for your lambdas. Will everyone get this right? Okay?
Yes.
Sweet, perfect. Our educated guess, because okay, we have no inputs here. This is gone. Now we have an output, but our output is due to memory or 0 input. Okay, we're just looking at memory. So YZIR of t is equal to our guess, C1 e to the lambda t. That is our guess. Okay? But we solve for lambda. Right? But what I gave you, my condition I gave you, is the following. I gave you, okay, when we have memory in our system, I give you this, minus 1. Okay? So all you're going to do, YZIR, is just look at this at time is equal to 0. So at y of 0, ZIR is equal to minus 1, is equal to C1 e to the minus 3 of 0. What is that? Done. Which means u of t. Do not forget that. Do not forget that. I'm going to write that down. Do not forget that. You will lose a point. Yes?
I thought at time 0, the output would always be 1, right? Negative. Instead just
That's my memory equation. Right now we're doing ZIR, the easiest part on the exam, okay? The reason why I did this model is to show you that if we have a 0 input response, 0, 0, this is gone. We're looking purely at our poles due to 0 input response. I gave you memory. There you go. So this is my memory condition. This right here is my memory condition I give you. Memory. Okay, this is what I'm going to give you, or Dr. Stuber would give you. Easy 5, 7 points on the exam. Done? Perfect. Now the hard part. And this is the trick I need to get to you. And now I'm going to bring back that motto. You're an engineering company. And I want you to build this piece. So what I'm going to try and do to hopefully get you this. Let me look at my notes because this is really, really important. Because if I don't show you this, you're going to get hurt by the second order. So, okay, before I talk about this. So we have C of t, right? I'm going to draw it a different way. I'm going to draw it in this format. You're probably not going to like this, but this is my way of doing it. Or this is the way Dr. Subaru was trying to show you in class. I'm going to do 3 poles to get you guys really prepared. A1, no. This right here, the bottom one's always minus A of 0. This one's always A of minus 1. A of 2. Okay? Get it? So, what happens if you're an engineering company, right? You're at an engineering company and you're building a feedback circuit, right? We're building feedback circuits, okay? We're doing a zero state response. Okay, zero state response of the poles. You're building purely this. How do you find the impulse response? There, okay? But the analysis that I'm going to try and get to you is we're not looking at t is equal to 0. We're looking at t is equal to 0 plus, all right? So what I'm going to draw for you guys is here's our time, right? Time goes forward, right? Here's 0 minus, here's 0 itself, and here is 0 plus, okay? Our Dirac delta is right there, okay? But we are here. Okay? So this system, right now we're at this position. Tell me, what is our output right here? And actually, before I do that, let me do this. 0. Okay? Now, our Dirac delta actually goes through this integral. What's the integral of a Dirac delta?
Unit step.
Yeah, it's just a 1. Just a 1. Yes, an area of 1. I know what you mean.
Oh no, that's not.
No, you're good, you're good.
The other way around. The integral of a unit step is a direct delta.
The derivative of the unit step.
Okay.
Because what happens when you have infinite slope, you get that spike, infinite Dirac delta. And what happens when you take, what's the area of all delta functions? 1. All right? So our delta function just moved. We're here. Now, assuming that we have no memory in our system, what's this? And then 0, 0, 0, 0, 0, 0, 0. So right here, I'm going to force this down everyone to memorize. Here's y of t. If we were to, okay, let's say this is dy of t, right? What happens when we integrate this? We get y of t, right? And working backwards, this is d2 of y, right? dt squared, right? And this right here is d3 of y of t. Does that make sense? So what are your conditions? Y of t is equal to 0 is this, is equal to 0. The derivative of y of t is equal to 0 is equal to this. It's the second derivative that gives you this 1. So the condition you're going to play with a third is basically t. Okay?
The second one is 1. Yeah.
So do you see a pattern right here? I'm going to show you the pattern right now. See this 3 right here? See this 2 right there? The pattern is the nth order, what do you call it? Condition for ZSR is basically d of n So that means what happens when we have a first order circuit? If n is equal to 1, what is our condition? Or wait. There we go. Sorry. There we go. Does that make sense?
Yes.
Nth order d of n minus 1. So that means if this is, we have d of first order minus 1, right? Right? What's this equal to?
Y of t is equal to
This is what people are going to memorize on the exam for a first order. And they're going to copy this for the second order. Don't do this.
that.
If we have a second order system, therefore, of 2 minus 1 is equal to d of y. That's how you get your conditions. Memorize this. Don't memorize this. Memorize this, okay?
So why is that the case?
Because we kicked our box. I made right here. I made this super hard, super hard. Third order equation.
So at t equals 0, the
T-
direct is at 0.
So right now I'm looking at t is equal to 0 plus, and right now we're here. What is our value here at t is equal to 0 plus? 0. There's nothing. The Dirac delta just went into here, got integrated. What's our value here? 1. Is that making sense?
No, I'm not following. 'Cause,
You're an engineering company.
the integral of the direct is 1, is that?
Yes, the integral of a Dirac delta is 1. We take the, what's the area of a Dirac delta? The integral basically takes the area of a signal. We get 1. We getting this? Because I got to keep going.
Yeah.
So what I'm trying to get to everyone's minds, please, I'm begging you, memorize this. Do not memorize that. I'm going to tell you, everyone's going to memorize this. Don't. This. Okay, he's going to throw a second order, I promise you, or a first one, either one. This is what you got to do. This is how he's getting it. Make sense? All right, that's exactly what I wanted to stress out for everyone. So now everyone's prepared for first, second, or third. Okay? Because for my exam, he threw me a first order, but that's because he threw something else that was pretty hard. But for your exam, because you guys don't have stability anymore, I probably guessing he's going to throw you a second order analog equation. So now, doing your quiz, I don't know, man. Let's hope he doesn't like give you something crazy, but it's going to be numbers. He's going to give you simple numbers. Can you implement them? Going back to your equation, if you're doing a zero state response, first look at your auxiliary equations. You've already solved it. Do you want me to skip this step? Okay. So now we're looking purely at the part that we're building. So I'm going to build you a part. Should I do this? what's the quiz that I had?
Yes.
-3, there we go. Right? This is our poles. Or feedback circuit, okay? You're an engineering company, what do? Kick your box. What's this? 0. What's this? And that's what you're gonna mess with. So looking back at our function d of y of t divided by dt plus 3 of y of t is equal to 0. We're looking purely at the feedback. There's no feed forwards. We're just building this piece. Part number 2. Okay, we're looking purely at this piece. Okay, we're looking just at the feedbacks. What do you do now? Yeah, why do I have to redo the work? You already done that with the ZIR. All right?
Oh, so it's the same. Okay.
Now, you're an engineering company. We just kicked the box. We're going to get the impulse response C1 e to the lambda t. However, you're an engineering company. I just told you this to kick this box. What are your conditions? This is your condition. Therefore, or h poles t is equal to 0 is equal to 1. Okay? C of, or just punch that in there, of e to the -3, 0. All right, and now tell me, what is your impulse response of the poles?
C1. Oh, I mean 1 to the.
Do not forget this. Got it? You just built the part. You're ready to put this wherever you want. What I'm going to ask you is, let's put this back into our feed forward circuit. And this right here is page 14, hopefully. Yes, this is a jam-packed. Yes?
Can I clarify something on the this one? So I guess I'm gonna. This is zero state response, right?
Yep, zero state response.
Where do we get the 0 derivative of y plus 3y equals?
This is
0?
purely the poles.
That's not zero input response because all the x's went to 0 on the right side.
We're purely looking at a part. We're just treating this as a piece. So what I'm telling you is, forget the zeros. We're building this poles. I'm just taking this part and we're building it at a different factory. We don't care about the feed forward path. Right now we have these poles. We're just building this right now. So
What I'm asking is like where we got that those two equals 0.
this equals 0
Yeah.
because there's no feed forwards. There's no B's. There's no inputs. We're just purely looking at the poles. This piece. This is a piece. We built this in an engineering company. The mindset I'm trying to get to you, when you're doing the ZSR, we're building two individual parts. The poles are its own part, which is a monster on its own, which has this crazy condition that you got to memorize or figure out how to get to. And the zeros, which are super easy. Okay?
So this has nothing to do with 0. Okay, yeah.
No.
This is zero state. We're just kicking boxes. We're just kicking. No memory. Kicking boxes. Okay? I'm stressing this out because you can do this anytime. Kick the finite poles. Finite impulse response. You get finite direct deltas. Kick the poles. You have to memorize this. Or figure out how to do all this condition stuff. Now put them together. Okay? So now you just built two individual parts for the ZSR, okay? So now, if I gave you H of zeros, right? H of poles, and I say find the ZSR, or what do you call it? Zero state response, right? What is a zero state response? It's an impulse response. What do you do with an impulse response? kick this box. That's it. What happens when you convolve the zeros with anything with the Dirac delta?
Anything back.
All right. And now, what is your output? We have the zeros right here. We have the poles that you just built. There you go. But note that this right here is an impulse response, right? So that means when we convolve these, or H, we're going to get purely the impulse response of the total system.
What is it?
H of n.
Why is it?
Because I'm treating this as a total system.
It's not H of T.
Huh?
It's not H of T.
H of, oh, sorry. It's getting late, man. The point is, the total, no, not total response, the total impulse response. We kick the box, we get feed forwards, we get feedbacks, we get a complete impulse response of the system. Got it? So now to finish this problem, well, what are our poles, or what are our zeros, first off? Actually, did I do that? Where is that? Okay, where did I solve? Actually,
You did zeros.
let me find it. Come on. Okay, see that right there? So when you're practically doing this problem, I will show you. Do I want to do this? Let's just practically tell you. So from the quiz, you have, I'm going to do this, shorthand, y plus 3y is equal to 2x plus 4x, right? Practically, h zeros, all you're going to do is, so here's your input, x of t is equal to the delta function. Ignore this, okay? So if we're looking for h of zeros, we're looking purely at the feed forward. There's no feedback. We're looking at c of n, okay? So just ignore this, okay? Or c of t, okay? All you do is just replace all the x's with Diracs. So 2d Dirac t plus 4 boom, done. 5 points. Now you have the zeros. Now you have the poles. Convolve.
So both H zeros and both H poles are zero state responses?
Yes, because we just kicked the box. There's no memory. No memory. Zero state means no memory, zero state. Zero input, we have memory. We're just looking at no inputs. All right? We have this. We have this. Convolve. So what I'm going to show you is, oh God, got to finish this now. But yes, today is a jam-packed lesson. 4 dt plus don't worry, I'll finish this soon. Convolved with e to the minus 3t u of t, okay? So we're about to convolve, right? So just to get this out of the way, what happens when we convolve the delta function with anything?
We get that back.
We get anything back. So 4 times e to the minus 3t u of t, okay? Plus, now I'm going to do this. U of t, okay? Because I'm going to do this on another piece of paper because this is a long process. All right? So you already got this. Hooray, hallelujah. Man, guess what page we're on?
16.
Holy moly, you see? That's why I told you Friday's lecture was so good. So now we're just going to analyze Analyze this, okay? If you forget this, you're not going to get this right. Okay? So analyzing that, I'm just going to skip steps. Minus infinity to positive infinity of... Yep. I'm going to keep this constant. I'm not going to move it, but I'm going to sweep this. By sweeping, I mean I'm going to shift it. As in, okay, put the 2 outside. E to the minus 3 t minus tau, right? U of t minus tau, okay? Times, I'm going to bring that delta function back. D delta of tau, d tau, okay? And what does this look like? This is the Dirac relative sifting property, which you can find in chapter 1. I don't remember what page that was. I think it was
page 82, example 1.56. I know that's page 82 though for sure.
okay. Review that. Remember all that stuff we were doing from chapter 1, quiz 1, like, oh, derivative of this, right? So now, what happens, the key is, okay, we're sifting one value. So that means, who cares about this? Who cares about this? We're looking at this. So that means, what we're going to do is 2. And d of d tau of, wait, put a minus there, because that's the rule. Don't forget that minus. It comes from this. Okay? That's the reason why it's there. Derivative of e to the minus 3 t minus tau, u of t minus tau, where tau is evaluated at 0. Okay? If you had a shift, you would have to evaluate at a different point. Taking a derivative, minus 2, we're going to take a derivative of this first. Minus, hold up, 3 e to the minus 3 t minus tau. Okay? And then I'm going to keep this guy safe. U of t minus tau, right? Plus, and then I'm going to keep this constant, e to the minus 3 t minus tau. Okay? Then I'm going to take a derivative of this. But what's the derivative of a unit step? There you go. However, we got to evaluate this at t is equal to 0.
Why is it plus and not minus?
Plus? This?
He held that one steady, and then he shifted.
Yeah, I'm taking, oh wait, yep. This right here is, I'm taking the derivative of this first term and then keeping this. And then this right here, I'm keeping this. And then taking a derivative of that. Alright? So now, when we have this is equal to 0, okay, just to format, plus 6 e to the minus 3t. Okay, get rid of that, get rid of that, get rid of that, get rid of that, okay? U of t, don't forget the u of t, plus e to the minus 3t d of t. Got it? This right here is for that convolution, this crazy stuff right here, which is equal to 2 d direct delta dt convolved with e to the minus 3t u of t. Okay, that's that part. Okay, and now for the finale. Holy moly. And we're back to the page I think we ended, 17. Where? Okay, let me try to figure this out. Y of t, which is equal to h of t. This is the impulse response. Also known as ZSR, is equal to, let's see, this mess right here, okay? 4e to the minus 3t u of t plus that answer that we just found right here, I'm going to write that on a different marker. 6 e to the minus 3t u of t plus e to the minus 3t d of t, okay? Okay, and then you can see this right here adds. You're done. You found your ZSR.
No.
Nope. This is just kicking your box. Now the total is equal to YZIR, which is the easy part you found. It took like 10 minutes or 2, plus YZSR, which is, dang, taking so long. I'm going to color code this. Let's use the red. Okay, ZIR, the thing that we found like I think 5-10 pages ago. Aha, found it. There, remember? Look, you see that? You see that?
Yes.
Don't go away.
E to the negative 3t times u sub t.
Okay? This right here is a ZIR, okay?
Yes.
Gosh. And here it is. 3t plus e to the minus 3t d of t, or direct delta, whatever.
We're not empty.
ZSR.
Yes.
Don't forget the t. Don't forget that. And then you see that this right here and this right here are in common.
9.
Right there's mega points.
I was just joking.
If you can do that, you're great.
Woo!
And you'll
Thank you.
get 100 on this exam. Are there any other questions?
So on an exam, say something like that, would it give us just a split or fill an equation out, like, find ZIR, ZSR, and that's
You saw how easy the ZIR was, right? Look at this. This page right here is purely the ZIR. One page.
That's if it's first order, no? Or
First order. So if it was second order,
then it would, you have to do C1, C2, and then you have to do quadratic before that to find lambda.
yeah, find the lambda, but I think it shouldn't be that bad. You'll just have more terms to convolve. See? And then the ZSR is,
I think like 17 pieces of paper.
okay? So point is, I would assume, because dang, this take long. ZIR is going to be the easiest thing I'm going to tell you right now. Get the ZIR. Everyone should get like the simple 10 points. But the ZSR is what I would highly recommend everyone study tonight and tomorrow. All right? Is everyone going to give me 100 on that assignment 4? It's literally, all right, can you just code this?
Bet.
Can you show me your hand counts? I showed that Word document, okay? Due tomorrow, 10 a.m., Tuesday.
Thank you, David.
Any other questions?
Now we good.
Have a good day.